Okay, this is residential wiring. We're going to discuss a little bit about electricity and a whole lot about its practical application. Okay, so first things first, you need to watch this video before you move on. Pause this. Go watch this. It's on the Google Classroom in this presentation. Go back to where the video is. Okay? Do that. Then come back and continue watching this. Okay, you did that? Welcome back. So first thing, there are two distinct types of current in when we talk about electricity. And if you want to break those down into house and automotive and electronics applications, that's kind of a good way to think about it. So DC is a current that flows from positive to negative in most conventions. There's some things that get a little funky depending on which theories you're looking at, but for our purposes, positive to negative, and that's it. Normally, we're using that in cases where, as I said, automotive, you open the hood, there's the battery, there's a positive red, there's a ground, which is black, and it flows from red to black. AC is a little different. It is actually switching one direction and then the other direction on and off, not on and off, but back and forth. And that's why you get this wave pattern that you can see right here. And that starts ramping up, gets to its maximum, ramps down, switches the other direction. And you can't perceive that. It happens 50 times a second in most places. It'll vary country to country a little bit, depending on how the electricity is generated and regulated. But it happens very, very fast. So the illusion is that it's not. So we break it down into three things. We're going to start with current and voltage. Electric current, I'm just going to read this because I think it's easier so I don't stumble over anything and make this more complicated. Electric current is the simple term are electrons in motion along a path. So no motion, no current. That's why if a switch is off, the circuit's open, you can't get a reading on that. Flowing the path may be a conductor such as copper, silver, and aluminum. We'll talk about that more in a second. And free electrons can be forced to move from one region of the conductor to another. Current is the rate at which the electric charge flows in a conductor. So how fast, essentially, it is. Voltage measures the difference in electrical energy between 2 points of the circuit. So if we look down here, water is the overall charge. Those are the flow of electrons. Pressure is the voltage. Flow is the current. So you can see right here, we've got our charge in this bucket. And then if we have the tap closed, we've got no flow. So see, current is flow, no flow. We turn it open, we open it up, and that flow, the pressure at it that it's coming out of there is the voltage, and the rate, so basically how fast it's getting through there, that is the flow or the current. So resistance is, as we pointed out in that case, is the valve, is the opposition to flow, is the what stops things. In a lot of cases, this is what we'd call our consumer. In the cases of lights, that's exactly what it is. There's a resistance because you have a light in line. And then the additional part is that it could be a motor, or you could actually have these things called resistors, which are basically there to slow down or to impede the flow of that electricity, and that's so that you don't blow something up. Maybe something needs a lower voltage and amperage to run, so we're going to use up some of that energy. Okay, so conductor, that's the thing that the electricity is flowing through, and normally this will be some type of metal or metal-like material. We know that water is a conductor and things like that. Examples of good conductors: aluminum, copper, gold, water, us. And that's one of the things you have to be really careful of whenever you're working with electricity. You do not want to become part of the circuit. If your heart, so you have a left hand and a right hand, and your heart is in between those two things. So if your right hand or your left hand become part of the circuit and you are grounding out on the other hand, that electricity is going to run across your heart. Your heart relies on electric impulses to beat. So it's going to interrupt that. And then you could potentially have death and death-like symptoms. If nothing else, it's going to be really uncomfortable. So insulator is the opposite of a conductor. It stops it. Rubber, plastic, things like that. Wood. Some are better than others. You have to make good choices, and a lot of those choices are made for you, like the coating on wires. So how do we get this power, this energy, this electricity? There are a bunch of different ways. Biomass, hydrogen, which is something you probably aren't super aware with because it's not really prevalent. What we do is we take hydrogen, which is H2, which is stored, and it runs over a membrane, and by virtue of doing that, it excites electrons, and you create electricity. Biomass, hydroelectric, oil, coal are all basically the same thing. You heat up water, it turns a turbine, and when it turns that turbine, it generates electricity. It's a generator. It's the same thing as the electric generator that you have, the gas-powered generator that you have when the electricity goes out, or if you're off camping somewhere and you're off grid and you don't have solar or some other type of electricity and you have a generator. That's how that works. Solar is different. Like hydrogen, you're using the sun to excite electrons, and that's how you create that flow of electricity. Regardless of how you do that, you have to get it from where it's made to where it's going to be used. Mainly your house, a business, a factory, or whatever. So we have our electric generation plant, switch yard that helps distribute it. We have our high tension lines. Then we go to a substation where we drop down from this higher voltage. It drops down, and then you can go to your normal electric pole, the power poles that you see everywhere in Vermont and around the country. It drops down, and then there's another transformer, and that brings us to the voltage that enters your house. And that will vary depending on where you are, but normally we're seeing single phase at the outlet, you're at 120, 110 to 120 volts, normally 120. And then the other amperages and the other voltages are normally about 240 at larger outlets. And there's some other stuff. Solar generation, the distance can be very similar, or it can be not so much. Like you can go right from your roof and generate all the electricity right there. So it's a very different system. So nuclear powered centralized solar, so you have these bigger arrays so that you can generate more and put it back into the grid or into the grid. Coal-fired plants, hydroelectric, it's all produced someplace else, then it gets shifted to the house. Normally solar, you'll see more localized production. Once you get in here, as I said, 240 volts, that's both legs. 120 volts is the other one. You'll see something like this. This is the meter socket. This registers how much electricity you use. And that's measured in kilowatt hours. So it's the number of kilowatts. It gets a little funky, and I still struggle with this. I have to look it up every single time. But a kilowatt hour is basically, you use 1 kilowatt over the course of 1 hour. And then yeah, it's weird, and I'm probably telling it to you wrong because I think I've got it, and then I look at it again, and it gets weird, as I said. But this basically is tracking that, and every electricity is sold in by the kilowatt hour, and normally what we see is that you are using X number over the course of a month, depending on the size of the house, the electric appliances. If you have an electric dryer and an electric stove, you're going to be spending more kilowatt hours a month to power those. If you've got gas, you're going to be taking that energy from a different source, which might be more or less expensive. Once you're in the house, on the other side of that meter, because that's measuring what's going into the house, and by I mean on the other side, they don't share a box, they're just directly connected. You see the service panel, and the service panel is the distribution center for electricity through the house. And there's a bunch of different ways to look at it, but what it does is it distributes the circuits. So like this 240 volt circuit to the AC unit, kitchen receptacle 20 amps, dryer 240, just to give you an idea, 15 amp circuit, it goes somewhere in the house. The size of the circuit, the amperage, the flow rate that can get through that circuit is dictated by what's going to be on it. Normally our little cell phones, alarm clocks, they don't draw that much. You don't need that much flow. But something like a stove requires a lot of flow, because what we're doing is we're taking that electrical energy and transitioning it into heat, because it's going through this giant resistor, which is the coil. It's creating heat. Standard circuit breakers, you're going to see a couple different types. These have varied through the years. I'm trying to go with a fairly modern approach to this so that you get an idea of what it looks like today out in the field. So you have these different types of circuit breakers. This is a standard circuit breaker. It has a amperage related to it, normally 15, 20 volts, somewhere in there. 30 amps. You can see down here, this is a double pole. When they get bigger, you need to have more room taken up in the box by them, because that's how they work. But with this, you can see that when it's on, it's an interrupt and it's a safety system. What I mean by that is that you can turn a whole circuit off so it's dead. So if you're going to work on it or something, it's safe. Nothing bad's going to happen. But on the flip side of that, it protects the circuit. If that flow becomes too much, if those appliances are trying to draw too much energy off of that circuit, it shuts off. And that's what this is down here. This shows the internals. That contact, if it becomes too much, it will trip the circuit, break the connection, and save everything theoretically on that circuit. We then also have arc fault and ground fault interrupt. That is for more sensitive stuff, essentially. Or if something could potentially get wet and cause a short circuit. Those two are for, as I said, specifically for instances where you want to have additional protection on those circuits. There are also regulations which I'm not super familiar with. I'm working on becoming more familiar with it, but there are different codes now that govern where and when those should be used, and they're being used more frequently. I'll tell you, I believe it's the arc fault. I've seen them put in. When the electrician I was talking to said that they are so sensitive if you're putting an arc fault, if you have the breaker in but everything else turned off, they'll actually trip if you disturb the wire too much. They're that sensitive, which can be a pain in the neck in some ways, but you know that you're protected with other things. So panels, this is what they look like in real life. They should be not like this. Everyone has seen a house like this. Whether or not you're familiar with it, everyone has seen these messy panels, and that's not good, because what happens is it's hard to work on. You want to add something, you got to move a bunch of stuff. Not only if you want to add something, but if something goes wrong, it's harder to trace out. If it's neat, it's easier to work with. So you don't have all this messy crap up here. You don't have all this. See, you're still going to have a little bit of disarray no matter what you do, because there's a lot of stuff going on. But you can make it neat, make it easy to use, and that's going to enable you to be better prepared for whatever is to come if you're adding something or removing something or servicing something. The additional thing is that as an electrician, this is really important. And the reason it's really important is because the best electricians have neat panels that are easier to work on, and they get reputations around it. The other thing, if you look over to the right, you'll see some old panels. These don't exist anymore. Well, they do, but they're not to code. This one on the far right is actually fused. So instead of having a breaker where you can just go down, oh, I blew the breaker, you actually have to remove the fuse and put a new fuse in there. This is just an older style that you'll see. So as I said, distribution. We talked about what goes in the panel. Now, what does it do? So distribution works by, we have the layout of the house while we're wiring it, and we know where the kitchen's going to be. We know where the bedroom's going to be. And we'll talk about what the specifications for certain receptacles in those rooms are shortly. But what you need to think about is, okay, if I have an office, I might need more outlets in certain places. You should always have a light so that you don't have to have a lamp in the room. That should be switched. And there are going to generally be places that you place certain pieces of furniture over other places. So if you have a living room, and it's generally a room like this. It's got an entryway here. It's got a window here. You're probably going to have it set up in such a way that you have the couch in the middle of the room and the TV on one of the walls. So you're probably going to want to. There's just certain ways that rooms are set up that, regardless of who owns the house, because you're not building the house for specifically how you're going to use it. If you're a contractor, you're building the house for any number of people. And yes, people can change what different rooms are used for what. That said, as I said, there are normally places where certain things will go in a room. Kitchens, as I said, same thing, lighting. Excuse me. Lighting. And then your different outlets. Your outlets are going to be at different heights. And again, as I said, we'll talk about the different heights for outlets and similar stuff like that. But this is all distribution. You shouldn't have circuits running like this circuit right here in light blue. Shouldn't be in this room, and then there'd be another circuit over here. Like, you can use them for different things, but try to get your circuits to be intelligent. You don't want to have like one going here and then one going off to a very far part of the house, and it share the circuit over here, because if something happens, you're not going to be able to say, oh, there's a problem in room A. You don't want to connect these rooms. You want to put them on independent circuits, or have multiple circuits going to one room. You'll see that these come out here a little bit. Like, these lights are controlled, and there's a light switch on the exterior or interior wall, depending on, it's a little hard to see. I don't know if it's a translucent or what, but you might have a light switch that's exterior of a room. Normally they're just inside the door, but you might have something that's auxiliary depending on what it is. Okay, so electricity, how this works, electricity comes in. We have the distribution from the panel, and then you figure out what the permanent fixtures are, like ceiling fans, sconces on walls, different lights, outlets. And the additional thing that a lot of electricians will do are fire alert systems, so basically fire alarms, as well as telephone setups, and cabling for internet. So those are some things that you'll also see electricians deal with, and wiring for in-home speaker systems. All those things are kind of at the same time. This right here, I don't expect you to be able to follow it, but you can kind of see, this is how this is a wiring electrical plan. And you can see where different light switches are. You can see where different fixtures are, and also how they're going to be wired. So you come from, where's the panel in this case? I'm having trouble finding it. But anyway, you come from the panel, and what lights are going to be attached to what, and where the switches are, so that instead of just being like, oh, this is how I would do this, you can have, and the same thing here. Where things go, how they're connected, etc. So the wire itself. This is important because if you don't get this, it's going to be a little bit hard to figure out exactly what you're doing. And I'm hoping we'll have enough time to actually get you to wire some stuff, but no guarantees right now. So the first thing, size of the wire. Big number means small wire. Small number means big wire. So 14 is smaller than, excuse me. Yes, 14 is smaller than 12. I was just making sure I was going to say that. So 14 gauge, and that's what we call it, is the gauge of a wire. You can see this, how 14 gauge and 12 gauge vary. And in addition to that, the number of wires in a outside sheathing, and this is what we call Romex. This is Romex wire. It has multiple wires. This is what we use for AC. You'll see some weird people using this in automotive applications. That normally means it's an electrician who normally wires houses trying to work on a car. I have a very good friend who uses wire nuts when he's trying to make a temporary fix on cars, and it drives me nuts. Don't use wire nuts in automotive applications. They'll shake off eventually. Cars move too much. But anyway, 14.2. So this is 14.2. 1, 2, 3 wires. Okay, let's take a look at 14.3. So there should be 3 wires. 1, 2, 3, 4. If you notice here, 14.2, there are 2 coded wires. These are what we call our conductors. That's what the 2 refers to. The last one is our ground. That's what this copper wire is. Copper, copper, copper. Copper wires in Romex are your ground. And the ground wire is used to carry current back to ground. If something bad happens or there's a little bit, it's trying to get that back to the source, to the ground, so it doesn't hurt anyone. That being said, that doesn't always work right. So we're trying to prevent fires, and we're trying to prevent injury. So black wire, white wire. Okay, 2 wires. That's 14.2. 14.3, there are 4 wires. 1's the ground, 3 conductors. Now you might wonder why, and you probably do, is why do we have that? Well, depending on the light switch or the circuit, you might need to have this extra conductor. This is your standard. The 2-wire setup is what you normally will see. And this is our hot, which is black, and our neutral, which is white. One thing you have to understand, electric circuits don't care what wire goes where. They have no feelings. They're inanimate objects. Oh well. Well, that being said, you can wire things completely backwards and they still work, but they have to be completely backwards. One of my very good friends, his grandfather, was a farmer, and he wired stuff whichever way he wanted to. So when we were working on a hay elevator about 10 or 15 years ago, we were like, oh, okay, this will be easy. You just put this, wait, they're all the same color wire, and oh no. So he just chose whichever way to wire it that he wanted to, and he just made sure everything else was consistent. Electricity doesn't care. This is to make stuff easy to work on. Okay? So, and we'll talk about what hot versus neutral versus ground versus other colors will be. But long story short, black is hot, white is neutral, copper is ground. Okay, so the outside sheathing also means stuff. White and yellow, that's our 14 versus 12 gauge. As you can see, 12 gauge is yellow, 14 gauge is white. Orange is a 10 gauge, so that's for 30 amp circuits. Black, 8 or 6 gauge, so really we're getting up into higher amperages, 45 or 60 amp circuits. Gray is a direct burial wire. It's a pain in the neck to work with because everything is sealed up. That's for putting directly in the ground so that you don't have to run conduit. You really should, but let's not get into that. So we talked about gauge, big number, small wire. Small number, big wire. 0, double aught, triple aught, big wires. Okay, let's talk about what these actually do. So wire color coding. Black is hot. Hot wires carry current from the panel to the device. Neutral wires carry the current back to the panel, completing the circuit. It looks like the DC circuit that we talked about, but it's doing something different while it's doing that. Okay? Just you're not going to be able to see it. You're not going to be able to perceive it. Just trust me on that. I wish there was a way for me to easily show. There is kind of, but let's not worry about that. Bare or green, depending on what it is. Those are your ground wires. Those help carry stray current back to the ground. And then, actually, I've forgotten to mention this. I know. Actually, never mind. And then there's the nomenclature on the side of it. So never mind. So underground feeder cable, MC metal clad cable. You'll see this in connections, especially in industrial connections. So where does this stuff go? First off, it's run in your wall. You try to avoid putting stuff on the outside part of the wall. So what we want to do is we want to place boxes. And those are where that's the only place we will mate. There's one. Sorry, before we get too far. So if we go back here, the red wire is also hot, but the other part of this is that with certain light switches, if you walk into a room, you turn the light switch on, you can walk across the room, you can turn the light off with another switch. That's called a three-way. And the way it works is you need an additional wire that's also a hot that will go in between those two switches. It's a little bit more complicated than that, but basically it's breaking the circuit in certain ways and reassembling it in others so that works. So back to the placement of boxes. Sorry to jump backwards on you. But anyway, so boxes are the only place other than the panel that you will mate wires up. You will not wire nut something and just let it dangle in a wall. That's a good way for the wire nut to fall off eventually, and you get a fire and then a lawsuit if you're the person putting it in. So when you put a box in, you're going from the floor to the center of the box, 44 inches from the floor. You're cutting holes at certain intervals so that you don't end up with wire just running willy-nilly through everything. Because if you do that, that's a good way for someone who goes to put a screw in to hang a picture to end up running into that. That's not a good thing. So you'll secure the box. That's where the receptacle or the switch or whatever, there are different types of boxes for different applications, and there are different boxes for different ratings. And as I said, we're talking about residential. This gets super complicated. And, in all honesty, if you're going to be going into this field, you're going to learn this very well. What we're looking at is general house construction. So as I said, there are different boxes for different applications. You're going to staple the wires to the studs. You can see this is our wall. That'll secure them. You don't want to pound that staple in so far that it cuts the wire. That's bad. And then on top of that, you want to make sure that there's a little bit of give there, because guess what? Houses move. And when the house moves, you don't want the wire pulling and cutting and being abraded by that. So this is coming directly from the National Electrical Code. A common height for a wall outlet is 12 to 16 inches to the bottom of the device. That's the ones on the floor. See, 12 to 18 to center. Countertop, 36 to 48 inches. It's going to change depending on the height of your counter and what looks good and how things are set up. Then wall, 48 to 52 inches to the center of the box. Okay? The other thing is, I thought that was right here. Oh, here it is. Yes. Generally, receptacles and outlet in it was covered up. Sorry about that. Habitable rooms shall be installed so that no point along the floor line measured horizontally and any wall space is more than 6 feet from an outlet at that space. The reason for this, that leaves a lot of flexibility for the room. Yeah, it does add a lot of receptacles, but it's not that much money in the construction process. However, you can put custom outlets in. Yeah, the code is saying that where they should be. If you have a specific reason, like you have a TV, you can have the TV at a specific height and have an outlet behind the TV so you can plug it in and keep your cables all nice and neat. So this is telling you where the outlets are so that you're never more than 6 feet away. That increases the flexibility of use for the room. You also don't want to have extension cords run all over the floor. You guys have been in my classroom. There are way too many extension cords hanging out. This is technically not to code because we do not. First off, extension cords are used temporarily. And the other thing is they're dangerous. You can trip over them. You can cause fires if they fail. Bunch of stuff like that. Okay, types of circuit, series and parallel. Series, the electricity runs through them. Parallel, you're energizing each one of these branches at the same time. The total resistance changes. There's less resistance in a parallel circuit with the same type of consumers. So these light bulbs are the exact same as these light bulbs. There's less total resistance in the parallel circuit than the series, and therefore the same amount of energy going through it will make it brighter. Okay, wiring, jumpers, and grounds. So when you're wiring something, you're normally going from your source to a first box somewhere, be it a switch or an outlet or whatever. It doesn't matter. You're normally going into a box. Well, you got to take that wire, connect it to the device that you're going through, and then keep going with it. So we use these things called jumpers. So you can see right here, we come from the box. This all has run through the wall. It's just out of it, so it's easier to see. You create this jumper, this short wire. This would be in the box that connects to your device. The wire carries on to the next devices down the line. Okay? That jumper is just a short piece of wire so that you can add basically a way for it to get off and then also use a wire nut. When you wire nut stuff together, you're looking for good connection in the wire and also that you're covering the wire completely. See this? This goes all the way down, no copper exposed. See this? Bad. That's a good way to get a short or a fire. So this is the same thing. So you can see this comes from the box into the box. This goes out of the box. You've got this short piece of wire here. That's a jumper. Same thing here, jumper, and the wires carry on. This is another video. Go to the presentation and watch it. It actually takes you through the entire process of wiring. Okay? Different types of switches, two-prong receptacle. Different kinds of switches and different kinds of receptacles. There's quite a few of them. Single pole switch. That's normally what you'll see. Turns the light off, turns the light on. Up, down, up, down. Double pole switch, basically two positions. Three-way switch, 240 appliance. Sorry about that. I was moving ahead. So double pole control 240 appliance. So it's a heftier switch. And then three-way and four-way switches, depending on what you're doing. These will allow you to have multiple points where you can control lights in a room. Two-prong receptacle, we don't want these. They're bad. If your house has them, it means there's not a ground, which means there's not a safety back to ground, so for stray amperage. Two-prong receptacles, bad. Grounded receptacle, these are pretty much what you'll see everywhere. Tamper resistant. These help, I can't remember exactly, but I believe these are the ones they hold onto the cord a little bit better. Arc fault, ground fault, surge suppression, and we'll get to the USB at the end. These guys, again, more added safety. We can talk about those, but basically surge. If you get the surge, this is going to protect sensitive electronics. These are more for, same thing, protecting stuff, but it's at a higher level. You still could end up with a fried piece of equipment. The arc fault, more sensitive than the ground fault, and it's the specifics of how they operate. USB receptacles. I personally think any new house should have these in specific areas, especially in bedrooms, because it eliminates the charger, so you won't have another potential fire hazard. You can plug directly into the wall. Okay, conductors and wire connectors. We talked about the size of wires. Depending on the size of the wire, the size of the box, and the wire nut that you're using, you can have a certain number of wires contained within there. That's what this is, box size. So 4" by 1 1/4" round octagonal box. So that's a 4" around with an 1 1/4" lip on it, I believe. You can have 14 wires. You can have 6 14-gauge wires. 12/5, 5/10, 5/8 individually. Okay? Wire nuts, gray, blue, orange, yellow, red. Again, color-coded for their use. It's a chart. Read it. Staples, boxes, connectors. Depending on the application, most construction applications are now using boxes like this. They're using plastic or plasticized boxes. That's normally what you see in residential. More industrial applications, or you'll see this kind of stuff, or older applications too. Things change, and also the use changes depending on what you're doing. Some of these can be used surface mount. Some of them can't be. And there's different electrical codes. I am not an electrician. I am telling you the general overview for general housing construction. I'm not talking about, on a Tuesday in April, this is what you have to use in this specific, super specific building. We also use these type of staples. They've got a little protector here to keep you from pinching your wire. Okay, wiring a switch. So we have our power source. We come up here. We come into the box. We would pull our wire out up here. We'd run a wire to our light bulb. 2 separate pieces of Romex. So we have our source, which is 1 piece of Romex. Then we have come from our box with another piece of Romex to our light. The light gets wired with a hot and a neutral and a ground. The ground normally is on the box, potentially could be on the light or the fixture, but you have this and this. One thing I have not mentioned yet, brass screws are for black wires. Brass screws are for black wires. So black equals brass. So the hot wire goes to brass. Again, it doesn't care, but this helps us keep everything consistent so you're not guessing. You wire this one, white wires go to silver. Think silver looks white, so white wire goes to silver. Green wires or ground wires go to green screws. So we have also copper. So copper or ground. So think green ground, go to green screws. They're painted. Black to brass. Silver is like white, so white goes to it. So here, a switch. We have our hot. We're switching this on the hot side. So our switch, we come from our power source. We have our black wire that goes to our black. We have a brass screw right here that goes through the switch, depending on which way the switch is actuated. Then that continues on up to the light. The neutral, or the white wire, is just connected. This wire from here, from the light, and the white wire from the power source, they get connected here. The green wire needs to continue on, but it also needs to ground this switch. So we use a jumper to connect the switch, and then we wire nut those 3 wires together, and we carry it on. When you do this, you are stripping off wire up until the box. that initial coating. And I can show you that at some other time if we do get to this in class. But you strip off that coating, the yellow or white coating continues on through the wall. The only place that that coating is removed is right here, and it's inside the box. You use wire nuts, and then you'd push all this back in. Okay, wiring an outlet. So, first and foremost, same thing. We come in here, we have our source, and that's it. Wherever we're feeding this from, that's all we need. We can continue on to another outlet or a light. We can power something down the line, and the way we do that, I'll get to in a second. So we have our source, we come in, we connect our white wire to our first silver screw, our black wire to our first black screw, and then our green wire is ground, our ground, in this case it's green, normally it's copper. We connect that here, if that's the end. If we're continuing on, we would take another piece of Romex, we would use a jumper here instead of just connecting it, and then what we'd also do is we would connect our black to brass, white to silver, and we'd carry on to the next outlet. This is how you wire a series of outlets. What you do is you start with one, and then you come in here, and then you go to the other. The other thing you can do is there's a little tab here. You can break that tab, and you can actually create a switched outlet. That's something you see in houses that was something that happened really frequently in older houses where there weren't lights put in the rooms. People just relied on a single lamp. But you can also do that for one of your outlets at your bedside table, because what you can do is you can have the light on in a room, and it's a switched light, so you have a lower light. So now we're going to put the two things together. This looks like a mess, but it's not, because we've talked about the constituent parts. So what we're going to do is we're going to have two wires come in. That's our Romex feeding from our panel. This right here is to another circuit someplace else. Ignore that. So you come in, first wire goes to silver, white wire goes to silver, first wire goes to black. Then right here, instead of coming off of here, we've decided to wire nut it. You could also come off of here, but what happens is our silver then goes up into our next box, our white wire then goes over into our next box where it meets up with the wire that's going to come from our light. Our black wire, because we're switching on the hot side, connects to the first brass wire, the brass screw on our switch. Then we go to our second brass screw, which is connected to that. So this is now hot. And then we connect everything up in our light, in the box that our light's in. So we come in, connect here. We're using wire nuts instead of connecting to here. That's fine. You can do either or. Then black goes to our switch. In our next box, our white wire carries through that box and connects to the neutral or the white wire from our light, and the light hot goes to the switch. That's everything on that. I just want you to be familiar with this a little bit. This is a three-way switch. We're not going to spend a lot of time on it, but this shows you how to hook it up. It also shows you how it works. So you have your hot coming in here, and you have a connection to your light. It switches here where it interrupts it. And these are the switches at either end of a room. And what that's doing is it's breaking that and reconnecting it so that it works, essentially. Okay, GFI can interrupt the flow of electricity through an entire circuit. And then this is, I believe, our last slide. This is just a reminder of how important this is. All of this stuff is a good way to create fire. Follow your codes. Make sure you know what you're doing. And if you don't understand, ask, because this is a good way to kill someone. All right, that's it.